Welcome back to the class. Today we're going to start from chapter 2. In chapter 2, we're going to talk about energy and first law of thermodynamics. The first thing we're going to do is to review what you learned before, probably in your physics class. We're going to review mechanical work and energy. Okay, the first energy you probably learned was kinetic energy. What is the definition of kinetic energy? We use Ke for kinetic energy. The definition of kinetic energy is 1 over 2 multiplied by mass multiplied by velocity squared. The unit is joules. Okay, so think of the scenario where you push one object over a distance. What's going to happen to the velocity of the object? The velocity will go up. In other words, the kinetic energy will go up. The change of the kinetic energy comes from the fact that you push the object over a distance. What is pushing an object over a distance? That is work. The definition of work, we use W for work. Work is defined as force, which is a vector, dot product, displacement. Displacement is also a vector. The unit for work is also joule. Okay, and then think of the scenario again. You push the object over a distance, that is work, meaning you do work to this object. What is the end product? The end product is the velocity of the object will go up, which means the kinetic energy will increase. So here we go. We have the equation. Work is equal to the change of kinetic energy. Okay, so let's do one example to refresh your memories. Here we go. We have a surface, it's flat and smooth. And then you have an object. You have an object. And then you push this object over a distance. However, when you push, the force is at an angle. The angle is theta. The initial velocity of this object is v1. And then after you push this object over a distance, we call this distance, let's call it d, displacement. And then at the end, velocity will become v2, and v2 will be greater than v1. And this surface, like we said, is smooth. So there's no friction. What we want to find out is the final velocity v2. How do we find final velocity v2? We can start from the equation we just developed. Work is equal to the change of kinetic energy. Alright, so let's start from the left-hand side first. Left-hand side is work. What's the definition of work? Force dot product displacement. How do you perform dot product? The magnitude of force multiplied by the magnitude of the displacement multiplied by cosine angle. What is the angle? The angle is the angle between force and displacement. Displacement is just horizontal. So what is the direction between our force and the horizontal position? Between the horizontal direction, and that is theta. So cosine theta. And then to simplify it, we can just write f d cosine theta. Okay, so that's our left-hand side. And then we go to our right-hand side, delta Ke. Delta Ke. What does delta mean? Delta means change. When you calculate change, it's always final minus initial. So what we need to write is the final kinetic energy minus the initial kinetic energy. What is the final kinetic energy? 1 over 2 times mass times final velocity, v2 squared. That is our final kinetic energy, minus the initial kinetic energy, which will be 1 over 2 m times v1 squared. Okay, so now we can plug them back into our original equation. Left-hand side, fd cosine theta equal to our right-hand side, which is 1 over 2 mv2 squared minus 1 over 2 mv1 squared. So because we know we're looking for the final velocity, which is v2, what you can do is to perform the algebra. In other words, move v2, the one you're looking for, to the left-hand side, and everything else to the right-hand side. So the solution is 2fd cosine theta over m plus v1 squared, and then square root of everything. So this is our final velocity v2. Okay, so that is the first thing we help you refresh your memory about. That is kinetic energy. And after that, the second energy you learned probably was potential energy. Potential energy. We use PE for potential energy. What is the definition of potential energy? Mass times gravity times height. We use Z for height, mgz. That's the definition of potential energy. Okay, so here let's do another example, which you probably have done in your physics class. The example we have here is free fall. Free fall. So this is the ground, and then this is the height. So you have an object which is located at height z1, and then the mass of this object is m. What it's going to do is free fall. Free fall. And we do not consider any friction from the air. Okay, how do we find the final velocity when it reaches the ground? Okay, so when the object free falls, what's going to happen to the potential energy? Potential energy will become lower because the height is smaller. What's going to happen to the kinetic energy? The kinetic energy will go up because the velocity of this object will increase as it falls. So kinetic energy goes up, potential energy goes down. What's the relation between those two? The potential energy plus the kinetic energy must be conserved. So the combination of those two must be constant. This is probably what you learned as conservation of energy in your physics class. The combination of potential energy and kinetic energy must always be conserved. Okay, so now if the combination of those two must be constant, then what we can do is what? Potential energy plus kinetic energy initial must be equal to the potential energy plus kinetic energy of the final. Because it's conserved, so it must be equal. Alright, so let's do our left-hand side first. What is the initial potential energy? mgz1. And what is our initial kinetic energy? It must be 0, because initially the velocity of this object is 0. It's not moving, so the initial kinetic energy must be 0. And then we move on to our right-hand side. What is our final potential energy? The final potential energy must be 0, because finally the object will be on the ground where the height is 0. If the height is 0, potential energy must be 0. And then what will be our final kinetic energy? 1 over 2 m times v2 squared, where v2 means the final velocity. And again, because we're looking for the final velocity, v2, so we perform the algebra by moving v2 to the left-hand side and everything else to the right-hand side. Our solution is square root of 2gz1.